Hey, welcome back. This video is more on lesson 7.1, which is mostly proving. So I just want to give you more examples. These ones are the longer one. The other video has like the beginner type of proofs. This one's slightly longer. So I'll see how many examples I can give depending on how long the video gets. All right, let me first get down to the identities. You have this provided to you, but it's always fun writing them. The Pythagorean and the third Pythagorean. And then also remember you can change these around as long as the move is a legitimate move, depending on the question. Then regarding our quotient, that's the first one. And the more you use them, you will notice that you would have automatically memorized them. Cosecant, secant, and our handy dandy cotangent. Then comes in even odd. Negative of sine theta is the same as sine of negative theta. That's the odd identity. Cosine theta is an even identity, so the negative theta dissolves. And we covered these in class. The tangent is also an odd identity, which means tangent of negative theta will equal negative of tangent theta. All right, here's the first example. This one says, show or prove all that is equal to sine theta plus cosine theta. All right, you got to prove that. So clearly left-hand side looks more complicated than the right-hand side, so I'm going to go ahead and get started with the left-hand side. I feel like I need to change this tangent to sine over cosine. And if I make any mistakes, you would realize that it's okay to make these mistakes. Sometimes we have to redo the whole thing again. So step number one, quotient is what I've used so far. Okay, when I look at the denominator, there's nothing much I can do with the numerator. So when I look at the denominator, like this is basically 1 over 1 and 1 over 1, and none of these match. So if I could multiply this by cosine theta, I will have the same denominator, which means this one could definitely take sine theta, and then sine theta. Has to be an even multiplication. I'm technically multiplying by 1, which is totally okay. So that's that. And then I am not doing much with the numerator here, but if you notice the denominator, we have been able to combine the cosine theta, and then in the numerator of the denominator, we have cosine theta minus sine theta, and then a big plus there. The sine theta, haven't done much to it. All I've done is combine this and combined the numerators, put them together. Now I do notice this is a fraction. To get rid of the cosine and the sine, you could either keep change flip, or if I multiply this by cosine, this cancels out, which is what I want to do. I want to get rid of the denominator of the denominator, but then technically you have to multiply the numerator also. Over here, to get rid of sine, it would be nice to just multiply by sine. That cancels out. Got to do that here as well to make it fair and square. Now cosine times cosine gives me cosine squared theta. Remember, do not square the angle. It's the trig function that has been squared. In the denominator, I have cosine theta minus sine theta still sitting there. And plus, this multiplies to sine squared theta over, I have sine theta minus cosine theta. Okay, I do notice that these two denominators are pretty much the same except for a negative sign, which means if I take care of the order, if I swap the order of one of them, I should be able to combine them. One more time, denominators are pretty much the same except for the negative sign. So, watch this. If I change this to cosine theta minus sine theta, which means cosine sine has changed and sine has turned into negative. I have basically multiplied it by negative, which means that plus needs to turn into minus to keep it fair and square, or else Al would have messed up with the equation. I have cosine squared theta still sitting here. I did nothing in this step except for took care of one thing. All I did was pretend you pulled out a negative from here, because once you do that, then the signs change. This will become negative, that'll become positive, and this automatically becomes cosine minus sine, which is what I wanted. But to be able to do that, I've technically pulled out a negative, and that negative that I pulled out makes the positive turn into negative. So it becomes a subtraction problem, basically. Now the denominators are perfectly the same, cosine theta, and I can go ahead and combine this because the denominators are the exact same. In the numerator, I now have cosine squared theta minus sine squared theta. And when you start seeing these squares, two things should come to your mind. There's a possibility that this could be the Pythagorean identity, or the other one is difference of squares. One of these should work within the scope of our pre-calculus, which means, let me look at the Pythagorean for a second. Cosine squared theta minus sine squared theta. This is not a minus, it's a plus there, right? So that directly doesn't convert it to Pythagorean identity. If I try and use difference of squares, which makes this, that's my a squared and that's my b squared, which technically converts to a plus b times a minus b, which means I have cosine theta sine theta and cosine theta sine theta, one with a plus, one with a minus, and this one's more tempting because you can clearly see that one of them matches exactly with the denominator, which is so tempting just to cancel it out. That leaves me with cosine theta plus sine theta, and that is exactly what we had here to begin with. Like I said earlier with proofs, and I explained that in class as well, you can only start with one side, pick and choose the side you think you can work on, the one that looks more complicated. Hence we picked our left-hand side. Of course, this is the left-hand side, and that's the right-hand side. And if I start with the left-hand side, I know the answer. This is my goal. That's the target. We want to reach to this destination using the identities or our general rules for addition and subtraction of fractions. And yeah, it matches up, hence we have proved it. One more time, do remember, anytime you see squares like this one, like this right here, anytime you see squares, chances are either Pythagorean or difference of squares. It just depends on the question. All right, moving on. Let's see, you can definitely squeeze another example here. Again, show or prove what? Let's say we have 1 minus sine v. So v there, theta, v, alpha, beta, gamma, I've told you does not matter. There has to be a letter following our trig functions, because our trig functions by themselves will have no meaning. If I just say sine, that has no meaning. It's sine of something, and hence we have to have something there. They're saying show or prove this equals 2 secant of v. And again, clearly we'll start with the left-hand side, definitely has more stuff going on. I'm like, okay, let me start with the left-hand side. Am I able to break any of these? The sine, cosine, sine, cosine. Generally, we're not able to break any of these. Also, none of these are squares, so I cannot use any of the Pythagorean identities. When it looks like you've hit a wall, and then of course, this will all boil down to just 2 secant of v. When it seems like we've hit a wall, we either multiply by the conjugate, which I have explained in class, that conjugate, if I have 1 plus sine theta, its conjugate is going to be 1 minus sine theta. Either we do that, or we will have to make our common denominators. Common denominator. One of those possibilities. Now, there's no point in multiplying by conjugate here because we have two of these, two separate denominators. What we can do is, if I were to compare this to any sort of fractions with numbers or regular algebra, let's say we have this. to make the denominator the same, this one needs to be multiplied by 5, hence 5 over 5, and this one needs to be multiplied by 12 and 12 over 12. And that's exactly what I'm going to do here. I'm going to make them the same, which means, let's use a different color here, which means this needs to be multiplied with 1 minus sine v, and this one needs cosine v, hence cosine v. Well, let's see what that gets me. For sure, that makes the denominator the same. So I have cosine v times 1 minus sine v. Sounds good. But then in the numerator here, we have 1 minus sine v whole squared. This is the one that's whole squared. It's more like a minus b times a minus b. Algebraically, that compares to a minus b whole squared. That's exactly what we did. Then on the other side, the plus, we have cosine times cosine, which is cosine square v, not v squared. So that's how far we've gotten. Now I also need to remind you on the side, a connection with algebra here. If we do have a plus b whole squared, or a minus b whole squared, that does not equal a squared plus b squared only. It does not equal that. There's a third term that comes along, which basically means a plus b times a plus b. And when you do the FOILing and all that stuff, it will end up being a squared plus b squared plus 2ab. Similarly, a minus b is a minus b times a minus b, and when you do the FOILing and all, this will turn out to be a squared plus b squared minus 2ab. It is super handy to have these memorized instead of going from here to here to here. It will be awesome to just have the formula going straight from there to there. The way I have it memorized is all I do is take the first one, square it, take the second one, square it with a plus, and then the third term comes from 2 times a times negative b, minus 2ab. I just have that in my mind like that. It saves a lot of time. We shouldn't have to FOIL over and over again. Why do I make that connection here? Because 1 minus, this one right here, look at that. That's a minus b squared. And that's what I'm going to do with it. I'm going to square it using one of these, which is a squared. Now my a in this case is 1, minus b in this case is sine b, and it's whole squared. I'm like, okay, a squared, which makes it 1 squared, plus b squared, which makes it sine squared v, minus 2 times a times b. And I did not write a because a was simply 1. So that helps me expand this part of the numerator. I've expanded it. Plus there's cosine squared v sitting there. Do not forget it, it's right here. In the denominator, we still have our cosine v and mine minus sine v. Continue. It's so much fun seeing these two together somewhere. Sine squared v plus cosine squared v is our handy dandy Pythagorean identity, the first and the most basic one. If you see them being added and they're squared, it all collapses to just 1. So what do I have here? I have this one, right? Bring that down just the way it is. Plus sine squared plus cosine squared v is another one, and then minus 2 sine v. What have I used here? Pythagorean identity. And in the denominator, still keeping it intact, sine v. And 1 plus 1 is 2, and minus 2 sine v. Still keeping the denominator intact. And now, again, one more algebra connection. This basically, if sine v was x, it's 2 minus 2x. 2 can be pulled off or pulled out as GCF, undistributing, which means I can pull out the 2 here. That leaves me with 1 minus sine v. 2 minus 2 sine v, when 2 is pulled out, does not leave behind that, that will be incorrect. You have to have a placeholder. If you've pulled out the 2, then there'll be a 1 left over there. And over cosine v, 1 minus sine of v, and it's so much fun seeing that one term of the numerator and the denominator are the exact same. So we have common terms there, which can be completely canceled. That leaves me with 2 over cosine v, but then we all know that this can be rewritten as 2 times 1 over cosine v. Keep the destination in mind. I remember we had a secant, so I remember that, which is nothing but 2 times secant of v. Hence, we have proved it. That's the most satisfying thing, like I always say. What did I use here? I have, let me erase this. I better justify my moves. Over here, cancellation. And the last one, converting here to here, was reciprocal. There we go. I know the video has gotten pretty long and I've only been able to cover 2 examples. I'm going to do one more. If you feel like you've gotten it, you can pause, stop the video here, come back later. But I want to continue. Another one. This one's using x's. They're saying prove or show that all this is nothing but secant squared of x. So show. Interesting. There are a lot of squares in the numerator, if you notice. So that brings in some sort of Pythagorean identity. So let's check it out. Honestly, if you look at this and that right there, that's again our favorite one. Yep, sine squared x plus cosine squared x. I'll rearrange it for you. Plus cosine squared x plus cotangent squared. And it's okay to rearrange if you see something coming up. So this clearly is a Pythagorean identity. Okay, now I'm going to convert that all to 1. So we have 1 plus cotangent squared x over another cotangent squared x. Again, keep in mind there are a bunch of squares here, so we might have to use more than one Pythagorean. I'm going to list here, I used one of them. 1 plus cotangent squared, that's also an identity. Yeah, right there. 1 plus cotangent squared is equal to cosecant squared. Okay, let's see if that helps. It may or may not help. Cosecant squared x, all of that converts to this. I still have this cotangent sitting here. Again, that's my goal, that's my destination. Everything somehow will disappear. What have I used here one more time? Another Pythagorean. Okay. You know, if I split this up, 1 over cotangent squared. Cosecant is 1 over sine squared. And then cotangent is cosine squared theta over sine squared, which means I can just flip it. Right? I could flip it. Or here's another way. That cotangent squared theta, 1 over cotangent squared theta, isn't that tangent squared theta? That's also reciprocal identity. And then you know that tangent squared theta can be replaced with sine over cosine. Still ended up with the same thing. Quotient and reciprocal, I use both. And you should be able to see the signs are going to cancel out. Cancel, cancel. I run into 1 over cosine squared x, which is simply secant squared x. Over here, cancellation. And we have proved it. Proved. It looked harder. It was not that hard because the numerator was kind of daunting here. It was like there's too much stuff going on. Here, this is what I'm trying to point to. There's too much stuff going on here, but then when I look closer, I'm like, wait a second, these two are nothing but 1. All right, one more, last one. Example 4. Let's see how long this is. Okay, okay, this one is very similar to the previous one. I think you should try it first yourself. Pause the video and try it. 2 cosecant of theta. So all this will collapse into 2 cosecant theta. Look at the previous one, very similar. Well, actually, no. It's the second one that was similar. Yeah, there we go. This one was very similar. Example 2 and 4. Okay. Of course, I'm going to start with the left-hand side. So again, the question says show or prove. Left-hand side, everything's broken down into sine, cosine. So this is one of those where, and there are no squares, so no Pythagorean identity. But if I multiply this by the other denominator, that will match up the denominators at least. Yeah, I highly recommend try it yourself first. And this one needs sine theta, and again, sine theta here. And now beautifully the denominators have matched up, so I can combine them. Squared theta. And these two, that's multiplication by default, multiply to sine squared theta. Okay, and then this one, these two, it's the same thing as a plus b times another a plus b. So that should be a plus b whole squared. Carefully call it whole squared. This is not difference of squares. Whole squared. That is, one more time, that is not difference of squares. Okay, I did that. Then I'm not going to touch the denominator. I'm going to open up the squared. Okay, let's open up the squared. I mean, yeah, you could have FOILed it up here, but according to me, this is a plus b whole squared, which, again, you either FOIL it or just use the formula a squared plus b squared plus 2 times ab. The sine squared theta just comes down just the way it was, and I'm now opening it up. A squared, which is 1 squared, plus b squared, which is cosine squared, plus 2 times a times b, which is 2 times 1 times cosine theta. Okay, and then clearly this plus this, that's 1 coming up there. That's 1. And then don't forget the one that was already sitting there. And then plus 2 cosine theta over cosine squared. Was it cosine squared? Oh no, it was never cosine squared. I bet you had caught my error before I did. This was never squared to begin with. Not a square. And not a square. Finally, I got my error. Okay, what have I used here? Pythagorean identity. Which one? Cosine squared, sine squared, they add up to 1. Also, I see 1 plus 1, so I'm just going to rewrite this as 2. There, 2. And then we're going to do the same thing we did earlier, that 2 can be pulled out. Remember, whenever you pull out, check your undistribution yourself. Like when you redistribute it, do you get the original back? 2 times 1 and then 2 times cosine theta. That way you'll make sure you haven't conducted any errors. Most common error here would be pulling out the 2 and then not putting a placeholder for 2 and writing this. Well, if you check your own the undistribution, 2 times cosine theta will give me that term back. Like what happened to the 2? So you will catch your own error that way. 1 plus cosine theta, and you can clearly see we have a common term in the numerator and denominator. That equals 2 over sine, so I can rewrite that as cosecant Cancellation here and reciprocal here. I had the goal in mind the entire time that it's just 2 cosecant theta, and we have achieved that goal. All right, I hope that was helpful. See you in the next video. Bye.